Unit 7, Stoichiometry. Phonetically, it's stoichiometry. Comes from a couple of Greek words, stoichion, meaning element, and metron, meaning measure. Specific definition, the study of the quantitative relationships that can be derived from chemical formulas and equations. Okay, now this is something that's best learned by example, so we're going to jump right in and do a number of example problems. Now, for each of the problems, we're going to be using this little flow chart. So this is mass of X, so X representing any element or compound being converted to moles of X. And of course, we know to convert from mass to moles or moles to mass, we use this relationship. 1 mole of any substance is equal to its molar mass. What will be new is we're going to be converting moles of one substance to moles of another substance, and that's where chemical equations will come in. This specific conversion is called a mole ratio. And then once we have done that, we'll have moles of that substance, and we can once again use the relationship of 1 mole of any substance is equal to its molar mass to convert that number of moles of that substance to mass. So please copy this down. It's a little tool that we'll be using to solve all of these problems. Okay, so let's jump right in. Now, the first example I'm going to show you is going to be a what's called full mass calculation, converting mass of one substance to mass of another substance. But as you'll see in subsequent problems, we need not necessarily go all the way from mass to mass. We might be given the number of moles of one substance and ask the number of moles of another substance. And for that, that's just one step. Okay, so here we go. Example 1. How many grams of potassium bromide can be produced when 10 grams of aluminum bromide react with excess potassium? Now, please, copy this down and pause the video as is needed. I'm not giving you pre-notes for this, so use the space bar to pause as I go along here. Okay, now the first thing we need is a balanced chemical equation. And so here it is. Aluminum bromide reacting with potassium hydroxide to give us potassium bromide and aluminum hydroxide. Now in this problem, what I'm going to do is use the chemical equation to summarize what the actual problem is. So it says how many grams of potassium bromide can be produced when 10 grams of aluminum bromide react. So I'm going to put the 10 grams of aluminum bromide, that's what we're given, 10 grams of aluminum bromide react. And the question is asking us how many grams of potassium bromide can we make? Now, the excess potassium potassium hydroxide simply means that we have all of it that we need. We don't need to worry about running out of it. So if I had 10 grams of aluminum bromide, how many grams of potassium bromide could I make? And so for our little flow chart here, the aluminum bromide will be X and the potassium bromide will be Y. And so we're going to be converting using these steps. All right, so here we go. Now, just like dimensional analysis, we will always start with what we're given. So we're given 10 grams of aluminum bromide. So that'll be our starting point. Now, it's really important that you also include the formula of the compound. Don't just write 10 grams. 10 grams of what? Aluminum bromide. Okay, now we're right here. So we want to convert it to moles. So, of course, all we need to do is to use this relationship. What is the molar mass of 1 mole of aluminum bromide? And it turns out to be 266.68 grams. So this will be our conversion factor. We know that because we want grams to cancel out. So this is just like a couple of units back on the unit in moles. If you were given grams of some substance, how do we convert it to moles? We simply use this relationship. Now what's different is we're not going to stop here. We're going to continue on. That one conversion will give us moles of X, but we're interested in moles of Y, and Y in this case is the potassium bromide. So the next step will be using the mole ratio. And this will be the first time that we mathematically use a balanced chemical equation to make a conversion. So for our chemical equation, we can see that for every 1 mole of aluminum bromide, we will make 3 moles of potassium bromide. And so that's going to be our next step, the mole ratio. Now, remember that the great thing about dimensional analysis is it tells you exactly where things go because you want your units to cancel out. So we had, at the end of this step, we had moles of aluminum bromide. So we want moles of aluminum bromide to cancel out. So in our mole ratio, moles of aluminum bromide will be in the denominator. So again, this is our mole ratio. It's the um, derived from the chemical equation. We have to have a balanced chemical equation to tell us the relationship between substances within that equation. So set up like this, we can cancel out the moles of aluminum bromide. So that's this step here. We have now converted to moles of Y, and again, our Y is the potassium bromide. Okay, but we want mass of Y, mass of potassium bromide. So there'll be one more step. So if we were to stop at this point, we would have moles of potassium bromide, but we would have moles of potassium bromide, but we want mass of potassium bromide. So we need one more conversion factor. Again, dimensional analysis tells exactly where things go. 1 mole of potassium bromide has the molar mass of 119.00 grams. We know that the moles of potassium bromide go in the denominator because they need to cancel out. And that's it. We have the mass of aluminum bromide. This converts it to moles. This converts it to moles of potassium bromide. This converts it to grams of potassium bromide. Now, when you type this into your calculator, remember you multiply by all numerators and divide by all denominators. It doesn't matter the order that you do it in, but what you do not want to do is multiply all the numerators, get an answer, multiply all the denominators, get an answer, and then divide one by the other. You're making your life much more difficult than need be. So please just follow my lead here. It would be 10.0 divided by 266.68 times 3 times 119 equals, and you would get 13.4 grams. We have 3 sig figs because we started with 3 sig figs. Remember that conversion factors won't limit the number of significant figures. It's always the number that we're given to start with. In this case, the 10 grams of aluminum bromide. That's our assumed measurement. Now, when you type this into your calculator, it doesn't matter the order that you do it. I could have gone 10 grams times 3 times 119 divided by 266.68. Again, it doesn't matter. Just remember to multiply all numerators and divide by all denominators. And please make sure that you're pausing the video and doing this calculation yourself. So you want to practice that. Okay, now again, this was a full mass calculation, mass of one substance all the way to mass of another substance. But let's do some variations. But I'm going to be using this exact little flow chart here for each of these problems. Okay, next problem. How many moles of water are needed to produce 4.56 moles of oxygen? And now for each of these, we'll need a balanced chemical equation. And so this is our balanced equation. How many moles of water are needed to produce 4.56 moles of oxygen? So we have the number that we're given, and the amount that we're given is the 4.56 moles of oxygen. And the question is, well, how many moles of water would I need to do that? Now notice when we refer back to our little flow chart here, we're given moles and we're asked for moles of one substance and we're asked for moles of another substance. That's just this one step. So that's a one-step conversion factor. Now, this is really helpful because it's really easy when you're first learning how to do this is to just immediately start bringing mass into it. But here, mass has no bearing on it. So we start with what we're given, 4.56 moles. And all we need to do is use the mole ratio from our balanced chemical equation to make the conversion. And our balanced chemical equation tells us for every 2 moles of water, we will make 1 mole of oxygen. Now remember, dimensional analysis tells us exactly how to set things up. We want moles of oxygen to cancel out, so it goes in the denominator. This is our mole ratio. We get this from our balanced chemical equation. So moles of oxygen cancel out. And so this is simply 4.56 times 2. And that would be the moles of water. Okay, let's try another. How many moles of oxygen can be produced from the decomposition of 5.25 grams of water? So this will be the same equation. This is the decomposition of water. In this case, we're given the mass of water, and we want to know how many moles of oxygen can be produced. So use the chemical equation to summarize the problem that you're given. So 5.25 grams of water. The question is how many moles of oxygen can be produced? And when we look back at our little flow chart here, we can see that we're given mass of a substance and we're asked for moles of another substance. So, oops. So this is our conversion that we're going to do, mass to moles of another substance. So we start with what we're given, the 5.25 grams of water. And so it's right here. We'll convert that to moles of water using the relationship 1 mole is equal to the molar mass. We know that the mass needs to go in the denominator so that it cancels out. That would give us moles of water, but we want moles of oxygen. So we'll need to do this conversion factor, which uses the mole ratio, which again is a 1 to 2 mole ratio. Moles of water goes in the denominator because we need to have moles of water cancel out. And that would be it. So 5.25 grams of water divided by 18.02 grams divided by 2 gives us 0.146 moles of oxygen. 3 sig figs, because we started with 3 sig figs. Now, maybe I haven't been emphasizing enough how you want to use the balanced chemical equation to summarize the word problem that you're given. It's really easy to kind of get lost in the word problem, to kind of lose sight of what you're given and what you want. But when you summarize it the way that I'm showing you here, it's really hard to drop the ball on that. So we have 5.25 grams of water, so it's clearly labeled here. And what are we after? We're after moles of oxygen. Okay, let's do another. And again, we'll use the same equation just to make it easy on us. How many grams of water are needed to produce 8.25 moles of oxygen? So we're given 8.25 moles of oxygen, and the question is how many grams of water will we make? So in this case, we're given moles of a substance, and we're asked for mass of another substance. So the moles of oxygen to moles of water to mass of water is what we're going for here. So we start with what we're given, 8.25 moles of oxygen. So we use our mole ratio to convert it to moles of water. Our mole ratio, again, moles of oxygen goes in the denominator because it needs to cancel out. Again, I can't say enough if you just pay attention to the units. Students will often say, well, I don't know what to do next. Just pay attention to the units, and you know that you need to have whatever units you begin with need to cancel out. So we have moles of oxygen needs to cancel out, so moles of oxygen goes in the denominator. Okay, now that would take us from moles of oxygen to moles of water, but we want mass of water. So we need one more step here. 1 mole of water is the molar mass of 18.02 grams. Moles of water go in the denominator to cancel out. So 8.25 times 2 times 18.02 gives us 8.25. I'm sorry, it gives us 297 grams of water. 3 sig figs, 3 sig figs. Okay, let's do one more. Now, notice what I'm doing here is I'm just showing you the variations of this flow chart here. But let's end this by doing, as we started with, a full mass calculation, going from mass of one substance to mass of another. Okay, so this will be the last one. A sample of water decomposes to produce 4.38 grams of oxygen. How many grams of hydrogen were also produced? So for this problem, they tell us that so we have a certain amount of water, and we don't really care about the amount of water that we start with. We know that we made 4.38 grams of oxygen. So the question is, well, how much hydrogen would we have made along with it? So it's exactly the same. We've given mass of oxygen, so we'll convert to moles of oxygen to moles of hydrogen to grams of hydrogen. I would encourage you to pause the video and see if you can do this yourself before I walk you through it. Okay, here we go. So this is a full mass calculation. We're given the 4.38 grams of oxygen. We need to cancel out the grams of oxygen. So 1 mole of oxygen is 32.00 grams. Remember, O2 is 2 oxygen atoms, so it's twice the molar mass of oxygen. That would give us moles of oxygen, but so now we need to convert it to moles of hydrogen. In our balanced equation, our mole ratio, for every 1 mole of oxygen, we will make 2 moles of hydrogen. So 1-to-2 ratio. Moles of oxygen cancel out. And so we would be here now. And one more step, converting moles of hydrogen to grams of hydrogen. 1 mole of hydrogen is 2.02 grams. Again, it's diatomic, just like oxygen, so we double the molar mass of the element. So 2.02 moles of hydrogen cancel out. So when you type this into your calculator, it'd be 4.38 divided by 32 times 2 times 2.02 equals 0.553 grams of hydrogen. Okay, now let me end here saying that this is exactly how you have to show your work. Sometimes students, when they hit this, immediately revert back to their middle school self. Remember, we have spent no small amount of time learning how to do dimensional analysis, learning how to convert moles to grams and back again. And so all of those skills that we learned need to be applied here. So we're going to be having nice conversion factors, units canceled out, sig figs, all of that good stuff. So the work that you're going to be turning in needs to look exactly like this. And this is not Massey's fussy way of doing it. This is the standard method to do a stoichiometric calculation. Okay, I will end with that. Now your homework, well, that's the end of notes, but your homework, I have another tutorial video that walks you through doing the very first problem. So please try to do the first problem yourself. It has multiple steps to it. And if you get stuck, certainly watch that video. All right, that's it.